Yes. Hello, Teresa, how are you?
Pretty good. How are you?
Very good, thank you. Hey, Max, how are you? Very good, thanks for asking.
Outside source.
Oh, that happened today. That happened today. Happening again.
It's a original story.
I mean, like, I thought it was used today.
No, so today we start prep.
Thank you.
It's not. Some people might be a little late.
We now have control over the lights in our office.
Oh, how nice.
So they're up there playing, trying to figure out the best.
Huh?
They're up there playing, trying to figure out like the best lighting and everything now.
So one can tailor it to certain areas?
Yeah.
If we get more grants, I have a plan or dream to establish noise canceling system in this aquarium room so that one can speak loudly without others hearing it. Like active headphones. There are systems for offices.
Will that help with like the fan that's above?
Yes.
Oh,
Right now we don't have allocation because it's like of an industrial price, but
Think they have, right?
Yep. That sounds like. Okay, like
got black from here, and then I found them on black. Never mind, I found out on Blackfoot. He said, that doesn't mean it will be on Blackfoot. I didn't respond to that.
I'm just gonna talk to him tomorrow.
Yeah.
Assuming he's gonna be there.
Yeah. Like a straight answer.
I still have an excuse of starting a little later before others are coming. If I would be a listener, I like the lectures which have a lot of talking and less equations, but on the other side of a barrier, I hate them because I need to think too intense and overview. The best is just writing down Hamiltonian and basically following up the consequences without thinking and commenting. It didn't change. I don't know about my failure or success in the instruction, but at least I have a plan. My part is done. Well, many thanks for coming and investing your time, and let me express admiration to those who helped with Science Olympiad. I think the intellectual effort and strengths of intellectual concentration is much higher there than on any of the classes. It's really broad and concentrated. I appreciate how things are going there. So what are we doing or planning to do today? I will announce the plan, and then we'll share screen and show a couple of slides, basically summarizing what we did yesterday in the lab. We are on the very important step, but each meeting we are on a very important step. It's important in its own aspect. We are in the transition from classical bath to quantum bath. So the course is organized telling to achieve a goal of modeling relaxation of quantum system to fight the major lie of quantum mechanics, to tell that system prepared even in the eigenstate or superposition of eigenstates will change its state and release energy, which happens all the time in real life. And there are several tools to achieve it. So we spent some time, the chapter 3 from the beginning of the class was chapter 1 from the after the break was on perturbation theory and Fermi's golden rule. And it is interesting to remember that rates of processes has been proved to be proportional to the interaction perturbation Hamiltonian squared, right? Times whatever density of states and some factors, but not first order, not third or second order. It is an interesting observation, and it will correlate with what we do next. Then we spend some time on looking on two-level system, its evolution over time, and interaction with pulses, with ODU tricks through rotating frames, interaction picture, and we noticed that there is a free induction decay. There is a like pi or 2 pi pulses, and then we decided that if one needs to describe realistic systems which have multiple similar systems, ensembles, and if one has interaction with outside world, wave function is not sufficient, one needs to go to the density matrix. And then we did set up equation of motion for density matrix. We established equivalent projection of density matrix onto Bloch equations, which can be expressed as adding and subtracting diagonal and off-diagonal equations of motion for density matrix. And then we got an interesting observation. If one just assumes that there is an ensemble of very similar, slightly different replicas of two-level system and generally any level quantum system, the equation of motion for density, one can replace literal summation over ensemble by writing down an equation for average elements of density matrix. So perform averaging over ensemble first and propagation in time second, which is already an approximation. Literal way is to first propagate each element and then add together. But there is a chance to swap them. It is very comfortable to do, but there is a price. As a result, one is getting additional terms in the equation of motion for density matrix or in the Bloch equation. And those are two terms of different nature: the longitudinal and transversal relaxation, if one speaks on the language of doublet two-level system in the NMR, but those are universal. So longitudinal because of the changing Bloch sphere, Bloch vector projection in z direction parallel to strong constant magnetic field, corresponds to population relaxation. So it's how the occupations of quantum levels change over time. And transversal, which corresponds to motion of polarization in magnetization in this NMR experiment, corresponds to dephasing, to loss of phase that is accumulated by any quantum system. But if there is a superposition, they come into destructive interference and lose coherence. So loss of coherence and loss of population are different, qualitatively different processes, and they are treated differently. So to take into account loss of coherency, we just performed simulation over ensemble and got that the 1 over T2, the rate of dephasing, rate of transversal relaxation is just proportional to the width of the distribution of elements in ensemble, or to the same way to the related to the density of states in the ensemble. The longitudinal relaxation was treated in a dramatically different way. We assumed that instead of static in addition to static, I'm looking for right word. There is an analog of word noise. Distribution. Randomness. Disorder. In addition to static disorder of the frequencies, there is a dynamic disorder of the interaction between system and the outer world. A few chapters before, we just assumed regular driving force, either constant excitation or pulsed excitation, where amplitude of the resonant field is changing smoothly. And now we assume that, same as we before, we assume that there is a, again, this word starts with letter D. Disorder, yes. In addition to static disorder of the frequencies, we have a dynamic disorders of interaction with outer world, which we modeled as the random coherence length, where nothing is changing, and random amplitude and phase. And then we noticed that if it is implemented, then we are getting new effect. Populations are getting decreased, right? In the so it is what we did in the lab. And when we try to describe it by pen and paper in the class, we treated it by making an argument that first order interaction Hamiltonian, if included into propagation, or like perturbation by first order interaction Hamiltonian, in average gives zero contribution. So one needs to go to the next order. And in the second order, generally speaking, one needs to assume that interaction events are happening in slightly different time steps. And roughly one can take just interaction amplitude squared, right? Which we derived last time, and which agrees very well with Fermi's golden rule. Right? If one wants to be very rigorous and meticulous, instead of coinciding interactions happening at the same time, one needs to admit that they may happen slightly one after another, and instead of just amplitude squared, one may need autocorrelation functions to see how much the signal agrees to itself after some time delay. So far, so good. And we verbally, we got all our goals addressed. If our focus is narrowed down only to two-level systems. But there was one observation during yesterday lab that prevents us from immediate celebration party and completion of the course. The solution, asymptotic behavior of solution, or solution in the steady state, if one assumes that time derivative is equal to 0, and then solving the algebraic equation, this two-level system would arrive to 50% equilibrium population between upper and lower state, which is one of the possibilities in the natural world, but it would happen only if the quantum system is interacting with a bath at temperature equals infinity. So at infinite temperature, two-level system will come exactly in the 50% occupation, and it is one of the reasons if one tries to bake a magnet, it stops being a magnet, right? So they come 50% magnetized up and down. Like if you have baking oven at home, it's probably sufficient to remove magnetization from home magnets. So this is good, but sometimes for practical purposes, we need equilibrium which is different from infinite temperature. Basically, it is the only reason to continue the course for a few more meetings. The classical noisy bath, I want to speak as much as possible, and then we'll go to writing or showing equations, does have terms in the equation of motion for populations which are equal for emission and absorption processes. So it absorbs and emits in the equal measures. And if you want to describe thermal equilibrium, which would correspond to infinite temperature, but if you want thermal equilibrium at different, a temperature lower than infinity, the rate of emission of releasing energy should be higher than the rate of absorption, which would result into equilibrium population less than 50% for excited state and more than 50% in the ground state. This imbalance of excitations and de-excitations is not possible to literally derive and justify based on the classical bath. So classical bath is failing because it is the same noise, same influence on transitions either up or down. So we need to design or get some deeper level of modeling that will create this imbalance. And this imbalance would come from considering the source of this noise as a set of quantum systems in the thermal equilibrium, which are following certain temperature. So quantum systems at a temperature which pass on their temperature. If our target, if our quantum system of major interest will be hotter than the bath, it will cool down. If it will be cooler than the bath, it will heat up. So this mechanism is missing in classical bath, and we will get all tools hopeful. Okay. It will be a poor backup through the camera, although there is nothing substantial yet. So I do not anticipate any substantial discoveries achieved by the end of today's meeting. we need to accumulate resources in sense like I do not put in doubt your fundamental education and knowledge. I hope that I also do not put in doubt my education, but same as computers, to perform some calculation, we need to load files from drive into random access memory. So we need to activate a couple of basic concepts that we will need intensely when going through treatment of the relaxations via quantum bath. And these concepts are on itself, they're like little building blocks. I'm confident that if there will be time and I invite any of you to the board, you will write it down with closed eyes or one eye closed. So, or if it will be short in time, I'll try to do it on my own. So the Boltzmann distribution partition function, which follows from summation of geometrical progression. Yeah, thank you, David. Taking survey physical chemistry. I don't know what is going on right now. Maybe it's also related to partition function and stuff, maybe not. But on the first part, we did a little review of summation of geometrical progression, partition function, and finding number of quanta in the harmonic oscillator, right? So I don't know about you, I may have forgotten it, so it's better if everything is brought up to the memory, because when we meet on Tuesday, we will need this actively. Also, a little administrative announcement. I do have an invited seminar in different, and we will not have next Thursday and next Wednesday lab. So they're postponed. If you need to make your plans and use this time for your personal benefits, please go ahead. I love to give Zoom online stuff, but unfortunately, I need to be speaking in front of audience at the same time. Okay, so Boltzmann geometrical progression partition function. Another concept is commutation of operators for harmonic oscillator, like and then these two concepts need to be connected, and we need to get to expectation value of number of quanta in the harmonic oscillator as function of temperature, and then to discuss how it can give a bridge to the concept of detailed balance. So if you fill this program within today, it will be perfect. And then it will create a little building blocks that can be merged together, and then we will rush through derivation of the crown of our class. Okay. Let me first and just remind you and to myself a couple of things that we completed last time. So I believe I shared screen, but maybe it didn't.
Well, I can see it on my computer. For some reason, it's not working on this computer. Yeah, I'm trying to, I told it to remove it. That way.
Oh, okay.
Respond, I've noticed.
Okay. So you see, this is a result of collective effort by multiplying two 4x4 matrices. And what is important that on the upper and lower far left, far right corners, we have this average of the amplitude of fluctuation squared. And it is an interesting pattern. So population, change of population for ground state is, I may have yeah, the signs should be fixed here, opposite. So it should be decreasing proportional to its own population and increasing compared to the population in the state. Draw. Minus here, plus there. Minus here, plus there. So just swapping signs. I borrowed it from the previous years when it was derived. Last time it was correct. So then connection to what we do is that transitions are equal here and there. They are of opposite sign but equal by amplitude. So it arrives to detailed balance at infinite temperature, and we need this constants to be different. So you probably recognize this thing is just pi/2 pulse applied to a two-level system, and here is the noise and the result of this noisy environment on the system under pi/2 pulse, where we have a lot of randomness in populations and coherences. But if one performs an average over ensemble, then in average, the populations get relaxed, right? And one can even try to fit this relaxation into exponential function. So if one projects it onto a Bloch sphere, so upon the pulse, then it shows a little dwarfs that digs a silo from the pole to the center, and it performs random walks as it typically goes for the noisy environment. And originally this noisy environment was mathematically designed for the Brownian motion observed on an experiment. Okay. So we are getting infinite time, but ideally we should get relaxation at any time between 0 and infinity. It is basically the goal that drives us. And before I return back to the board, here is the little video that I was partially expecting Lola to show during her talk, something like this, but she did much more and much deeper analysis. So what is autocorrelation function? It needs to be introduced because we will be using it actively. So what do you see? I'm not sure if you have time for interview, but just show a little science if everything is perfectly clear, if it is unclear image that you hate, or if you have basic understanding but not sure how to verbalize it. No idea at all. Okay. More or less. David?
I want to do the thumbs down for the hate, but
have you seen this demonstrated by Aaron?
Yeah.
Hadassah? Okay. Lola? Okay. Oh, it's better. It's like almost perfect. Steven? Does the figure make sense, or it is completely irrelevant? What do you think?
I think it makes sense.
Okay, so what we have here is that there is the same function which is explored at little with zero offset and then with some offset in respect to itself. So this blue and red functions are identical, They just selected to be something reasonable, like Gaussian wave packets with some oscillations. And at the time zero, when they coincide, one can perform the following mathematical operation to do an analog of dot product, but dot product in a space of multidimensional functions, basically overlap, same as one does orthogonality of functions in quantum mechanics, right? So multiply these two functions and integrate over the whole area of definition. So if functions are normalized and if their time offset is the same, it will give maximal overlap equals 1. As soon as they depart from each other, the dashed line, which corresponds to the degree of their overlap, or we need integral of this degree of overlap, may get negative, may get back positive, but if they are localized functions and far enough from each other, they become 0. So this is graphical definition of autocorrelation function. So how the function correlates to itself. Make sense? Okay. So yeah, the rest is what I'm expected to draw things. So done this. So I don't know what to say. If the object has a temperature less than temperature of the bus, it will soak. There will be stream of heat hitting it. If the temperature is higher, then the stream of heat will be in the opposite direction. So I think it goes very much in agreement with thermodynamics, which is probably offered in the 759 right now, right? You get some more advanced like entropy, enthalpy, laws of thermodynamics, but the idea is here. But now this system is quantum, so it has quantum levels. So it will be either exciting or de-exciting, like absorbing or emitting, based on the temperature of the bath. Thermostat. And it needs to be quantum thermostat because of our primary object is quantum, and to explore and describe their interactions, they should be on the same foot. We already made an attempt to do classical bath, and one can mimic results of quantum bath with classical bath, but it will be cheesy approximations. The best way is to literally consider both bath and our primary system as set of quantum levels. Classical, quantum, transversal, longitudinal, So by now we did practice classical bath. We know for sure that transversal relaxation doesn't have any relation to temperature. You do not have any temperature dependence, and likely since you have just static distribution, it corresponds likely to zero temperature. For the longitudinal, so we have either minuses or question marks for finite temperature and infinite. For the longitudinal, we know for sure it works well for temperature equals infinity, and we have either minuses or question marks for zero temperatures and finite temperatures. And our goal is to have pluses everywhere. Limit of zero is limit of infinity and limit of finite temperatures. I think there is nothing valuable is written here, so I can stay on this board and erase it. Okay. So one of the exercises in this class was to discuss and involve effort of class attendees as saving team who saved this ship from sinking, to bring in the Hamiltonian of interaction between matter and radiation field, right? You remember this? It was introduced. Yes. So so in interaction between matter and field, one started from and then it can be expressed in the terms of where we do not take into account temporarily the squared, and we focus on the dipole of the matter and vector potential of the field. And if one carefully processes this Hamiltonian, one can bring it to some constants, volume, and then momentum can be represented through the creation and annihilation operators, vector field of creation and annihilation operators of the field, and the matter can be expressed, if it is only two-level system, as plus conjugate. Right? So by now we put major effort into this direction of formalization of our efforts. And the reason is that interaction between matter and field was discussed in finer details for longer period of time. For chemistry applications, there is a quite important aspect of interacting between electronic levels and nuclear vibrations. In this situation, one is there is a way to derive the Hamiltonian of interaction, the electron H nu and electron to nuclear. There is a way to express this interaction as the quantum part of nuclear kinetic energy. And I would love to speak a little longer about this transition, but it is quite lengthy. In approximate way, it is reduced to the matrix element for electronic state I, electronic state J, response of electronic states to modification of interatomic distances times momentum and there are some additional constants in front. So I'm skipping very appetizing and interesting story in between, and we may speak if there will be time before the end of the semester or delegate it to one of the talks. I believe by now Lola has selected a talk maximally related to this stuff, right? So if you want to have it not as a matrix element, but as an operator, one can set this as IJ, formation of all ions. There will be factors with mass, and one can put into here IJ plus IJ II. So transitions between electronic states I and J, which are so if we want to make this operator of system to bus interaction fully on the full quantum language, we can use definition of momentum in terms of creation and annihilation operators. So let's take it as quantum operator, and then we can put it as proportional to use letter B B sub I bigger minus B sub I. And to be correct when we need the dimensionality factor, which I just do not want to fail in front of the audience, but it will be a combination of mass of an ion, frequency of the oscillation, and Planck constant. So they will pop up in the numerator and denominator of this of the square root. And then the non-adiabatic coupling A by J with small a comes as a coupling constant, and then there is a quantum operator of electronic transitions. IJ, JI. Actually, lowercase a uppercase. So, what do we see in this writing? What is important for our consideration? And later on, when we will be deriving things exactly and specifically for practical applications, I will take an effort of cleaning up all constants and making sure they're correct. We can summarize and identify a common motif of these two interaction Hamiltonians. Sorry for counting on you too much. Thank you.
They're several years old.
So, our little duck in the pool is our quantum system, right? Two-level system, or maybe something more complicated. So, for photons, we have our primary system with letter S, or I can try to draw this duck in the pool. If we are speaking about electronic system interacting with nucleus, it is the same structure. We do have this system operators that correspond to transition between electronic systems. So there are some constants in front, and then there is, well, to be general, one needs to assume that there are several modes, same as here. There is a combination of quantum operators related to the bath. Right? There are combinations of quantum operators related to the bath. And in this sense, dissipation of energy from electronic degrees of freedom, either in form of electromagnetic wave radiation or in form of heating up nuclear motion, are mathematically equivalent. So we do have the interaction Hamiltonian as a summation for both degrees of freedom, summation of electronic or system degrees of freedom. And then there is a coupling constant, which depends on indices for system and bath. And then there are bath operators of the first order, and there are system operators of the first order. So by this time through my life, I didn't express curiosity to check if other degrees of freedom would match this common motif, but at least two situations match it. And if we, if the electronic degrees of freedom could be quantum levels or spin projections, then it is a variety of objects to deal with and describe. So this system to bath interaction Hamiltonian, I'll try to minimize use so that they don't dry out, is quite universal, and one can perform some mathematical derivations based on this generalization. When we go far enough into deriving the equation of motion of density matrix for system under interaction with a bus in a thermal state, we can go back and add specifics and check if I made any failures and errors here, fix them and take care of them in a very precise and accurate way. But the general idea is there. So B linear coupling. So it's linear in both system and bus operators. There are above linear terms, but if the interaction is weak, they are droppable. They are negligible. And if the linear terms are leading, then the higher terms can be dropped. So it's there are motivations to assume this type of interaction, even if there are some additional interactions. It will be a leading term providing major component to the rate of energy dissipation from the quantum system. So I am going to, with your permission, to keep red box and erase everything else. There is not much. We agreed on the idea. And I need to do several more comments before we have a break. I'm going to say something which is not absolutely perfectly without proof and justification. It's more like connections and observations of similarities. So if we look at the Fermi's golden rule, so rate of a process will be something like 2 pi h. Do we need to h bar squared or h? Or we don't care about the constants right now? So interaction Hamiltonian squared, density of states, of final states. Right? Second order time dependent perturbation theory. Do you remember? How does it look like? Well, it definitely includes, well, I think
The one integral plus, yes.
it's
No, it's two integrals, yeah.
d tau 1, d tau 2 from initial to tau 2, tau 2, tau 1, 0, t, initial state, if you speak about wave function. Delta ji if the corresponding minus 1 over h bar squared, something like this. But there is interaction Hamiltonian comes twice, right? If we are looking for our last experience of the non-zero contributions to the longitudinal relaxation in this two-level system originating from noisy bath. So it is like 2 omega squared fluctuations, which actually interaction between our system and noisy bath, right? So we do have second power here, second power here, second power there. An interesting fact. Second power rules. Now, and if we are approximate, then it is just second power. If we want to be rigorous, they are evaluated at different times, right? Now, if we plug in this stuff into either one of those, so V interaction of tau 1 times V interaction of tau 2. So it will be summations over bath probably twice, like B prime, summation over the system also twice, because we want them to be independent. Then it will be G S B G S prime B prime. And then it will be an interesting observation. So you will have B of time in time tau 1, B in times tau 2, S in time tau 1, S in times tau 2. So right now, we do see that following general observation from our previous experience in the previous months would mandate us to explore second order of interaction Hamiltonian, even if it is cast in the full quantum way, right? And if we are mandated to explore it at different times, we would observe a necessity to work with products of the operators of bath and operators of system evaluated at different instances of time, right? So I, with wholeheartedly and with all strict plans and resources, intend to perform complete derivation from the very beginning. So right now we are not doing derivation. It's only some building blocks that are expected to make our life easier when we meet on Tuesday and subsequent meetings. But there is an observation that we need to get skills to identify properties and manipulate with products of operators of bus and operators of system. And eventually we need to be able to evaluate them at different instance of time. Okay. So that is here. And if we are focusing on this box of bus operators, if we assume that there is a substantial average or ensemble or of quantum states, it will be creation and annihilation operators, which are offset from each other by a certain time interval. So A dagger A, 0, A dagger, A dagger, A dagger, A. So not, so not. So if you will learn how to find expectation values of such combinations of operators, and time dependence can be accumulated in the interaction picture as accumulating phase, right? So if you get a way to find expectation values of such functions, we will be ready to do all steps needed to achieve the goal, to achieve the quantum relaxation that will work at any temperature. So quantum correlation functions or correlation functions between operators. We were already exposed to such combinations for like spin operators, S plus, S minus, at different times by London Stock. He wasn't visualizing it as figures, but he provided answer in form of equations. So it's something that is not 100% new. We saw it a little bit before. So it's a good time to have a little break. And in 4 or 5 minutes, we need to look on geometrical progressions, commutations, and number of quanta as function of temperature. How are you? What?
I was limited enough to
Whenever you are ready. That's okay. I'm preparing for seminar talk next week, and I will be away traveling. So yes. So yes. So I will not be grading until I return anyway. So
We had a game there.
do not worry.
Every time we went down to City Hall, I couldn't get a straight answer.
I didn't hear. Uh-huh.
I saw it on a, in the last year.
Not worry. That's okay. That's okay. It's not for the like record or grading. It was only to support discussion and help everyone to understand what is going on. So don't worry. That's absolutely fine.
One day where I can send notifications.
If there is a deadline, I will try to match it. Just send reminders. But I do not want to be the last. If all other recommenders have already submitted, I will do immediately. If I'm not the last, I will do it way back. So keep me informed. I'm
They don't know who you are. Like, or not, they do what they say. They were researching and said, but. Everyone else. No, nervous in the shower. That's. Okay. I know that's an option. They may have come in today. I've been teaching all morning, so I don't know. You're whatever. People do this. It's not the end thing. Came through. Another 121 of labs 50. Just only mine is much higher. Real.
Everyone is here. Please vote. Let's focus on class to see the votes. Just yeah. Please vote if you have an idea what will be the next. And I plan to do everything myself, but please vote if you basically understand what is going on and you're ready to come to the board and continue.
less if you give me a direction.
Without direction, if you see the directions,
Well, I mean, it's a harmonic oscillator, obviously, but
more than that. So I expect Tori, Max, and Adam to have this information activated in their random access memory. It was refreshed in 759 related to black body radiation. So I promise you will not go to the board, but would you be able to go and continue? Do you have an idea what is going on and how to continue? So what do you think is next?
Talk about temperature dependence. State occupation.
Okay.
It's,
Okay.
Just the ground state for just for two states.
Okay. And I believe then the next thing will be to find exact analytical solution for the sum. Do you remember what it is, or what is the strategy to get it? Mm-hmm. Appropriate. Yeah, I think we can go to the board.
Yeah.
Okay, thank you. So to rederive this. Hadassah, any ideas what it should be or how to rederive it?
I don't know, it leads to a Boltzmann distribution at the end, it leads to a Boltzmann distribution at the end.
Hmm?
A Boltzmann distribution. at the end.
Well, this is the Boltzmann distribution.
yeah,
Right.
Area distribution, right?
It is a boson, it's harmonic oscillator.
Oh,
So it's Bose distribution. So one can go into Wikipedia and find answer for Bose-Einstein distribution. Yes, it is a good plan. But if there is a aircraft or ship accident, I'm thrown alone on the inhabited island, and suddenly I need Bose-Einstein distribution without Wikipedia and internet. What should I do?
So
What's the plan? So energy is the same, right? It's a major beauty of harmonic oscillator that it has the same energy offset, and there are so many possible analytical solutions for the oscillator.
The arrow is more as well, sorry, ground state.
For unharmonicity, but this is ideally harmonic, even if it is not realized in nature. It is so beautiful mathematical model that one needs to take as much benefits as possible. Okay, I feel a little bit better. I thought I'm behind everyone in class, and you already know the answer and you know the derivation. Let's do it together. I promise that you will not go to the board, but just cooperate on this thing. So formally, energy of harmonic oscillator includes zero phonon or zero photon energy, like 1/2 h bar omega, right? But for in mathematical sense, one can select zero on origin equivalent to the ground state. If you just save a lot of efforts. So if you accept this, then this so Boltzmann distribution, Boltzmann factor, and it should be normalization, right? Summation of all populations must be 1 because we look only on one harmonic oscillator, right? And then if we just perform summation, this Q goes out of brackets, and then one can multiply left and right by Q. So summation should give this normalization or partition function or statistical sum, whatever is terminology. So summation over n e to the power minus h bar omega n at. Summation e to the power minus h bar omega over kt to the power n. Okay. So if temperature is noticeably small, so if h bar is bigger than kt, then all this exponentials to the power minus of big number will be smaller than 1. So it is, we can call it x, which is smaller than 1. Then we have q summation of n x to the power n. So x to the power 0 will be 1 plus x squared plus x cubed plus x. So there, it is one of few things in the world that has analytical answer. And it is in the limit of x is smaller than 1. Let's call, let's guess that it may be 1 over x plus 1. Maybe. I truly do not remember. Let's prove it. So this one can be called summation of 0th order. This can be summation of 1st order. This one is summation of 2nd order, right? U0 equals 1. U1 equals 1 plus x. U2 equals 1 plus x squared. U3 1 plus x squared plus x cubed. Let's identify some features and common motifs. Can we play a game under name recursion? Is there any relation between qi and qi plus 1? So can we express q2 as function of q1? How?
Q1 plus x squared. Like,
Okay. It's possible. 1 plus x squared. But is there any alternative ways? 1 plus x times q1. Would you agree? So we take x out of brackets, and then we will have q1 in there. Okay. Now, if can we express q3 as function of q2?
plus x times q2. They're following the same pattern.
Let's check. I'm not a quick thinker. Let's just expand and double check if it is correct. So Q2 is 1 plus x squared. It will be 1 plus x squared plus x cubed. Yeah, it works. So now we can assume that q sub n plus 1 will be equals to 1 plus x times q n, right? Can we get any benefit out of it? Let's think. What can we do? We can subtract. There should be something that will be dropping in the limit of n equals to infinity. So let me. Mhm. How can I miss it? This is like way number 2. This is way number 1. We always can tell that at the same time q n plus 1 is equal to q sub n plus x to the power n plus 1. Right?
Yeah, set equal.
Okay, let's set it equal and see what happens. So q n plus x n plus 1 equals 1 plus x times q n. And then we can put q on all q's on the left. U n 1 minus x and everything without q on other side. 1 minus x to the power n plus 1. And then we do have u sub n will be 1 plus x n plus 1 divided by 1 minus x.
Yeah. Yeah, that one can't be right because that's bigger than 1, or sorry, smaller than 1.
So you see why I'm tending to rederive. It's I do not count on my memory. It's so easy to solve the sign. And now if we do a limit in n goes to infinity, then small number into the infinite power will be 0. So we have 1 divided by 1 minus x. Okay. So the q, I don't know what letter q stands for. Quotient. Norm, partition functions, that's some, but it is not called n, p, or s by some reason.
Sure. Because I think that this was something that like Boltzmann and crew were doing.
Okay, I should check. Yeah, a lot of German word starts with W. Is Q? You should check. So U is 1 divided by 1 minus e to the power minus h bar omega over kt. So it's not a universal answer, it is only for harmonic oscillator, right? I'm going to erase everything, maybe except diagram, because it is beautiful. Well, not in my implementation, but intellectually beautiful. And this answer. And we still have a few items on our plan. Is it okay to erase? Probability that level n is occupied is e to the minus h bar omega n kt divide by q. How interesting. If it is divided by q, then it will be multiplied. Really? I was expecting this part to be in the denominator. I'll double check. But what? And I do not have it in the notes, but we'll do it anyway. So why? What is the goal? It's quite normal to forget who we are, what is our goal, and why we spend all this efforts. It's not because we like to perform summations of series. So the goal is to provide building blocks to describe release of energy from a quantum system to either photons or phonons. We cannot, it's insufficient for us to use the classical noisy bath. We want the bath to be quantum because we want a detailed balance. We want to system to interact with thermal bath at a certain temperature to arrive to a temperature between 0 and infinity, not only one of those. And as we have noticed by looking at the Hamiltonian, which I didn't erase there yet, it is quite standard, quite normal to assume that the bath is represented by harmonic oscillators. So it is not my frivolous decision at the last minute before going to the class. If you think about natural objects that do serve a role of a bath that interacts with our primary quantum system, they indeed can be approximated as harmonic oscillators. So the electromagnetic radiation in the resonator, it is oscillating. It is an oscillator. It like harmonic coherent state oscillating. It was designed for it. It's electromagnetic radiation always oscillate. Waves, circuits. It's quite standard and normal. Interatomic distances. If we do not have explosion or vivid reaction coming through the barrier, typically molecules and solids and nanostructures have stable chemical bonds which perform small oscillations near equilibrium. So though they are oscillators. So for quite general range of implementations of a heat bath, we can assume that our electronic quantum system is coupled to a pool, to a bath of harmonic oscillators of different frequencies and residing in thermal equilibrium at different temperature. So our connection to our overall overarching goal is that we need to speak about one of the harmonic oscillators representing the bath. We need to dump this oscillator into equilibrium thermal state. Therefore, we play this Boltzmann distribution. So we assume that all coherence has already gone. It's not in the ground. It's slightly excited because it interacts with other oscillators. Philosophically, one can immediately raise the question and provoke the whole class discussion from completing by explain the mechanism how the energy redistributes between different modes of the bath. It's an interesting question, and one needs to have another pieces of matter that absorb and re-emit, and then equilibrium is established. But if we have a black body radiation, it's typically an object that obeys thermal distribution, like solar light. So what is the connection? What do we need from this model? How to what do we need from this quantized and thermalized harmonic oscillator if we set up a goal to describe relaxation of electronic system? We do need to find the number of quanta, average number of quanta in this oscillator. Why? Show number 3. Yeah, thank you, David. So let me attract your attention to this little cloud in the shapeless box. So if we would take in the Hamiltonian of system to bath, if you will process second order interaction, we will run into combinations of bath creation and annihilation operators. Through your tenure in this class, you already noticed the rotating wave approximation. So quantum systems accumulate phase, and corresponding operators accumulate phase. And they accumulate phase clockwise or counterclockwise, depending on whether they are operator itself or it's conjugated. We typically used one operator representing electronic system, another was electric field accumulating phase, and we were taking only those terms where there are counter productive compensating phase accumulation. Same thing in here. So if you do have operators like A and A, they accumulate phase in the same direction, create very high oscillating frequency, double frequency compared to optical light, that in average will give negligible effect. So both AA and A dagger are not contributing. One can defend a thesis of importance of including these terms, but it will be like less than 1% or less than 5% in all practical applications. So it is quite safe. We will see it, that it is quite safe to drop these terms. So by deriving an equation of motion for density matrix of quantum system interacting with a thermalized bath of either photons or phonons, harmonic oscillators, we will stay only under combinations where one of them has dagger, another doesn't. And by commutation relations, So a dagger is a dagger a plus 1, right? And there is a way to prove it if we put this equation into doubt. The way to prove it is to one of the ways to prove it is to express creation and annihilation as superposition of position and momenta, and position and momenta do not commute because momentum operator is a derivative. So derivative and x and derivative over x by swapping the order they're not equivalent if they apply to a function. And from there one can pull this result, or there are some alternative ways to prove. But if this is correct, then second correlator, second combination of creation and annihilation operators is equal to the first one just by added by plus 1, right? So in fact, we need only the first one, a dagger a. So it is something universal that we need to take care of. Now, what is the meaning of this a dagger a? I'm not proving, I'm just calling for some memories. Would you agree on this?
I think so, yeah.
Okay.
Just wanna go over first and then raise it. So
Yes.
you don't hear the ground.
So if we are at certain quantum state, if you go down and go back, we arrive to the same state. And then it's a way to identify what was the energy of the state. I know I'm not logical and I'm not proving these things. There are ways to prove this equation, but if you believe this, and if you divide h naught by h bar omega, and if you assume that our origin is set up in this way, then how can we interpret this operator? What does it correspond to? So a dagger a tell us, would it be depending on
Photons we have.
yes, so number of photons or number of excitations, or to which quantum state we are excited. So operator of number of photons, number of photons. And if you want to be a little bit more general, we can photons or phonons, right? Number of excitations in harmonic oscillator. So from this point of view, to serve our overarching goal to have building blocks to compute relaxation of the quantum system in the interaction with the heat, we do need to apply statistical thermodynamics methods for thermal equilibrium in order to evaluate number of quanta in a given bath mode. And this result will be used as an input, as a building block towards getting quantum relaxation of primary system, of electronic system. And this is a place where information about temperature will be stored. So our goal is to get relaxation, which is temperature dependent, to arrive to detailed balance, to different proportions between ground and excited, depending on temperature. So this will be an input that we will later use in our overall results. So there is a task, well, task for myself and for you just to lean back switch the lights off, take popcorn and observe. To use this statistical sum partition function, and was another word for this. What else? Doesn't matter. To find the expectation value of number of quanta in the bath mode. So how do we do it? So we expectation value of n is summation probability that state number n is occupied times actual number n, right? That's it. The rest are a little mathematical exercise. So I think it is the last thing for that we need to complete today. I want just to have a breath of air before deriving. Let's focus on the class and make a mini interview. Who has an idea how to derive it? Or who has the approximate answer?
I've seen it.
Okay.
I actually worked it out myself, at least not with these prediction and annihilation operators.
But David suggests that Adam knows how to answer. No? But any ideas? Do you see any symmetry? Turn to the camera and say, David. Max, have you any memories? I'm positive we did it together 2 months ago in 759. If you don't remember, it's my favor as an instructor.
You started me off.
Sorry?
My brain is thinking on n equals 2 things. So to put those two things equal to each other.
Which things?
So the bottom line and top line.
Okay.
Oh, sorry, the second, that. The bottom line is the one right above it, my bad.
Okay. Okay. Well, here is definition, and this dagger operators, they carry quantum information. Right now, for the next 15 minutes, we give up quantum mechanics. We practice statistical thermodynamics. So we don't care about creation and annihilation. We just have, we do not think as chemists or physicists. We just solve mathematical stuff. So let me do the next step. 1 over Q. So Q is not involved. It's only a function that depends on temperature, and it doesn't have n, right? So it can be same as like with integrals. If the function doesn't depend on integration variable, it can be placed outside of brackets. And here we have Boltzmann n times Boltzmann factor minus h bar omega n et. To practice this, the trick that I'm going to invite you to follow, some people in physics admit a little change in the notation, which has nothing to do with math or science or physics or chemistry. It's only a notation, but it flips the mind and makes things to go in a little smoother way. So what if we call 1 over kt as a new variable beta?
Saves a lot of writing.
Not only. So let's write this thing and look on it once again. So u summation n e to the minus beta h bar n. So any ideas, any observations of symmetry? I see Adam is smiling. Do you know what is next, or you just it's like a cloudy? I saw it in my dream, but I don't remember exactly what.
It's like a dream. I've seen this all before. I've seen it all play out.
Okay, a little exercise, and then you will be, each of you will be able to finish. I promise I will finish today. So exponential alpha x dx equals
Alpha X.
alpha e alpha x. So if there are two variables and we take derivative in respect to one, then the second one will pop up in the front. So if you do see exponential and one of the variables in front of it,
Starting to look like a derivative.
yes. So 1 over u summation d beta e minus beta h bar omega n, and then n will pop up in here, and h bar omega will also pop up in here. But since we do not have it, we probably need to put h bar omega in the denominator.
And
Huh?
and the negative sign.
Okay. Sounds good. Okay, I'm going to erase things above this line and continue. So expectation value for number of quanta, 1 over the partition function. Summation. I'm just rewriting. Minus 1 h bar omega d beta e minus beta h bar omega n. Does beta depend on n? On the, so you can put it outside of the bracket. So 1 over q d beta. Also you can put minus h bar omega, and then summation n h bar omega, and now we can come back to our KT. Right? And borrow. Okay. Are we familiar with the summation?
That's cute.
Right. Which is a good analytical function that would allow a human being to take a derivative. What's a surprise? So number of quanta, 1 over q minus 1 over h bar. And then we just take derivative over beta of the function 1 divided by 1 minus e minus beta h bar omega. I think now I can erase the bottom and continue. Yeah, we should be finished in a few minutes. So this expression can be treated as function to the power -1, right? So now we need to remember our freshman calculus skills and take a derivative. -1 omega over q. So derivative of a function in a power, like x to the power n, derivative would be what? Power decreases by 1, right? And the factor comes up front. Now n equals -1, x equals this 1 minus blah, 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 right? And then one needs to take the derivative of the secondary function. So you have -1 factor, then 1 minus e minus beta h bar omega to the power -2. And then we have d beta of the 1 minus e minus beta h bar omega. So derivative of constant is 0, and derivative of exponential, as we recently recited, will be exponential. So e minus beta h bar omega minus h bar omega, and then we have minus staying from here, right? And then the rest is boom, 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 boom. So minus minus plus, minus minus plus. This stuff can go into the denominator. 1 minus e minus beta h bar omega. 1 over h bar omega 1 over q equals expectation value of n. In fact, this is the answer. It's just not. It is not beautiful, right? So we need to massage it to please human eye, and bring it to the form that can be memorized. So I'm going to erase everything above the line, and we are very close to the end. So q is 1 over this subtraction. 1 over q will be flipping the stuff into the nominator. So 1 over h bar omega. In the nominator, we have h bar omega e minus beta h bar omega. Here we have, let me keep the same color so that it will be trackable. 1 minus e minus beta h bar omega squared. And this one will be 1 minus e minus h bar omega beta. So we suddenly observe that it is the same factor. What a surprise. So this one is gone, and the power 2 is gone. H bar omega appears here and there. What a surprise, they cancel. So expectation value of number of quantas as function of temperature will be E minus H bar omega KT 1 minus E minus H bar omega KT. And if one wants to play lazy and write few symbols less, one can divide left and right upper and numerator and denominator by the same factor. So 1 divided by E to the power plus H bar omega ET minus 1. So let's analyze what we have. So temperature, expected number of quanta. If temperature is infinite, you get infinite denominator. What? No. If temperature is infinite, H bar omega over temperature is 0. E to the power 0 is 1. 1 minus 1 is 0. 1 over 0 is infinity. Reasonable. Infinite temperature, infinite number of quanta. Okay, one test is passed. 0 temperature. 0 means H bar over 0 is infinity. E to the power infinity is infinity. Infinity minus 1 is infinity. 1 over infinity is 0. Test passed. What else can we check? Maybe H bar omega equals KT. So E to the power 1 will be about 2.7. 2.7 minus 1 will be about 2, a little different, roughly. So about 1/2. So if we have temperature of bath approximately equal to the temperature of to the frequency of oscillator, it will be halfway occupied between ground and first excited state. N equals. So we are going to use this equation as a building block for the when we meet next time in class on Tuesday. We will not finish all derivations on Tuesday, but we will get major definitions, and then there will be additional mathematical procedures in second Tuesday from now, because Thursday is skipped. And then we'll see if we want to finish early or do a couple of applications if there will be additional class, or tie the loose ends. So everything I planned is done. If there are any questions, I'm very he puts you on the spot. I'm happy to answer, but if not, feel free to disconnect and depart. All good? Many thanks, David. Much appreciated. Did you go to all, both?
Yeah.
Because I, without bad intentions, I put
Their mind because they're Office Depot.
Thank you for consubstantial contribution to the class.
Come in handy when you're on a university, like.
Right. Either show everyone or just finish the meeting.
Are you gonna be at school?
I was giving Adam special attention. You can tell he desires it because of his hair.
Like after the,
Okay.
after the kid.
Yeah.